So today we will first discuss those questions. We'll go deep into those questions, learn something from it, and then we have to cover up viscosity today somehow, and then we can finish it off. And then the next day we'll start with surface tension, right? So then I'm going to start now. Discuss the first question. An oil drop falling through still air at its terminal velocity v suddenly explodes to form a number of identical droplets. The subsequent terminal velocity of the droplets would be. So how would we go about doing this question, right? So now, first of all, we have to understand the question properly, right? So they're talking about an oil drop. It's falling through still air at its terminal velocity, right? So there is an oil drop that's going down with its terminal velocity, Vt, right? Let's mark it as V because they have told that the terminal velocity is V, and it explodes to form a number of identical droplets. So it's going to explode to form n number of what? Identical droplets. So we have n number of identical droplets. The subsequent terminal velocity of the droplets would be, okay, so the droplets would have what? A velocity, a terminal velocity of, let's say, v dash, because we don't know the terminal velocity of the droplets. Now, I need to relate this larger oil drop to what? The smaller oil droplets. What is the relationship? You know, it's volume, right? So if I think of this as having a radius r, this is going to have a radius of r dash. Now tell me, last time we proved a particular equation of convenience. What was that? Terminal velocity v was equal to what? 2 over 9 r squared rho minus rho dash g over eta. So in the question that we were discussing, in the theory that we were discussing, we said rho is what? The density of the object. What's rho dash? What's rho dash? Density of the fluid. Because this object was going down the fluid. Of course, these can reverse depending on whether the object is going up or down, right? So then, can you see, when you look at these two situations, that is when you observe the larger oil drop and when you observe what? The smaller oil drops, both of those, right? Both of those situations are going to have the same viscosity because we are sending these oil droplets in the same medium. So coefficient of viscosity is the same. And of course, both of these situations have oil drops which have the same densities, right? So then the density factor is also the same. The surrounding medium is also the same. Therefore, rho dash is also the same. And it's, of course, under gravity. So now, can you see, I can say terminal velocity is proportional to what? R squared. Because everything else is a constant, right? So now if you look at this second situation, where you have these numerous oil droplets. Okay, I can mark the terminal velocity of a small oil droplet v dash as being proportional to what? R dash squared. So now I have v is proportional to r squared and what? V dash is proportional to r dash squared. Now I need to relate the terminal velocity of a small droplet to the terminal velocity of the larger droplet. Okay, so now can you see I need to find out a relationship between what? The two radii. And that's an easy matter. Why is that an easy matter? Because I can relate the two volumes together. The volume of the larger droplet is equal to what? The sum of the volumes of all the tiny droplets of oil. So then, of course, you know how to write the volume of a oil drop, which is what? 4 over 3 pi r cube. And of course, I can write the volume of a smaller droplet as what? 4 over 3 phi r dash cube. Now, do you understand? Okay, the volume of the larger droplet is what? 4 over 3 pi r cube. And that should be equal to what? N times the volume of what? A smaller oil droplet, which is what? 4 over 3 pi r dash cube. Now do you see these cancel off, and r to the power 3 over n equals what? R dash to the power 3. Now what can I do? I can take 1/3 power on both sides, right? Then what do I get? I get r dash equals what? R to the power 3 over n to the power 1 over 3. And then r dash is equal to what? R n 1 over 3. Okay, now tell me, I have found out, haven't I, r dash in terms of r. Okay, I have found out r dash in terms of r. Now you tell me, you see, I got this expression, v is proportional to what? R squared, that's the terminal velocity of the larger oil drop. In the smaller oil drop, v dash is proportional to what? Terminal velocity of the smaller oil drop, which is v dash, is proportional to what? R dash squared. But I can write v dash as being proportional to what? R dash squared means r over n over 3, entire thing squared. Okay, so v dash then is proportional to what? R squared over n 2 over 3. I can think of this as the second expression, this as the first expression. Of course, there's a constant, so I can write v dash equals k r dash squared. Like that I can write, right? So I don't have to write the constant, because you know, when you divide these two equations, there is already a constant. So I'm going to divide 2 by 1. Then what do I get when I divide 2 by 1? Actually, this is not 1. This is 1, right? So when I divide 2 by 1, what do I get? V dash over V equals what? R squared in 2 over 3 divided by what? R squared. Then this R squared cancels off. Then V dash over V equals what? 1 over n 2 over 3. And then from this we can say V dash equals what? V over n 2 over 3. Is that understood?
Yeah.
Right. So
Correct.
everybody else?
Mine is correct. Mine is correct.
Okay, brilliant. Okay. So now I hope everybody else is fine as well. So I
Yes, sir.
am going to go on to the next question. So a lead ball of radius A is fired from a toy gun in water in a large swimming pool, as shown in the figure. The densities of water and lead are ρW and ρBB, respectively, and the viscosity of water is eta. If the x and y components of the velocity of the ball at a certain instant are Vx and Vi respectively, then the magnitudes of the corresponding acceleration components at that instant would be. Actually, we can solve this question in like 30 seconds if you think about it. But then again, of course, you can solve this the long method as well. But I want you all to understand first the long method, and then we will see how quickly we can get the answer. Okay, so now let's explore and dwell into this. So if you observe this, they're asking from you the magnitudes of the corresponding acceleration components at that instant. Now you see, when you think about this motion, as shown, they marked Vx. Vx means what? The horizontal component of the velocity. And what is Vy? The vertical component of the velocity. So this is the velocity, and you're going to break that down into the x component and the y component. Now, you know, viscosity is this resistance to movement within the fluid. If this is a bullet, actually. So, right? So if a lead ball is fired like so, right? What do you see? When it's going to go towards the right, because the horizontal velocity component is there, which drives it to the right. Okay, so which means there is what? A resistive force occurring backwards, viscous force occurring backwards against the motion of the sphere. And of course, can you see that this sphere is going to go downwards, right? It's going downwards. So if it's going down, then the resistive force should be acting upwards. Fx is the resistive force acting in the horizontal direction, and then Fy should be what? The resistive force that is acting in the vertical direction, Fy. Now listen carefully. Now I need to find out Fx and Fy. First, compartmentalize your question into segments, then assimilate them together, right? Break it down into the simplest substance. Make it simple. Okay, so now if you observe this, if I think about the x direction, I need to think about the external unbalanced forces operating in the x direction, right? So what is the only external unbalanced force occurring in the x direction? That is the resistive force, right? That is the only external unbalanced force that is occurring in the x direction. So now, if you see, I can apply Ficus MA in the horizontal direction. But of course, the force is there backwards, is occurring towards the left. And do you know what this force is? What is that force? 6 pi r eta Vx. What is Vx? The horizontal velocity. And that equals what? The mass of the object, which I can write in terms of the volume of the object and the density of the object. Now tell me, what is the volume of the object? 4 over 3 pi. Actually, this radius is given to be simple A, right? It's given in the question to be simple A, so I'm using simple A. So 4 over 3 simple A cube. And what is the density of the sphere? Rho PB. And then now I have what? The mass. So if I multiply the mass by the acceleration, I get the acceleration in what? The x direction. So now, if you want to find out the acceleration, of course, you have to subject it. That's a simple matter. So here to the power 2, right? So then you already these 2, this is 3, and then pi cancels off. What do you see? You get 9 eta Vx over 2a squared rho PB equals what? Ax. Okay, now tell me, okay, we have found that. From that, how many answers can we eliminate? 2 and 5 can be eliminated for sure. Okay, now I need space. Actually, I thought there's enough space. What I can do is y'all can zoom onto this at home. There's a PDF, so you can zoom onto this. I'm going to make it smaller and keep it on the side. Now I'm thinking about the vertical direction. So now tell me about the vertical direction. What are the external unbalanced forces acting on the sphere in the vertical direction, right? So of course, you have the weight acting downwards, which is mg. And then you have the upthrust acting upwards. Now, when you're trying to go down, there's anyway a viscous force, Fy, acting upwards. Okay, so you can see three forces are acting on this sphere in the vertical direction. That's why you should always be precise about the direction that you're choosing. But you see, it's going down, right? So now I need to apply Ficus MA down. Now tell me, what is the resultant force? mg minus Fy minus what? U. That is equal to what? Mass times the acceleration. What is the mass of the object? 4 over 3 by a cube rho pb, right? Multiplied by g is the weight, and minus what is the viscous force occurring in the vertical direction? So we have the vertical velocity, right? So then we need to put what? 6 pi a eta by minus what? Upthrust. What is the magnitude of the upthrust now? What's that? 4 over 3 because volume sunk, right? Multiplied by density of the surrounding fluid, right? So multiplied by gravity. So then 4 over 3 phi a cube rho water g equals what? So I've taken too much space again. I need to make this smaller. Okay, it's equal to what? Mass of the object 4 over 3 pi a cube rho pb times acceleration a. Now simplifying this, you have to be very careful. Take it easy, go step by step. Did you all get the conclusion up to this point? Understood?
Yes.
Okay.
Yeah.
Now, I can divide by 2. This is 2, this is 2, this is 3, this is 2. And of course, I can multiply by 3 as well, right? The entire equation, I can multiply by 3. Use these techniques. This helps you to solve questions much faster. And of course, whatever you can cancel, please do cancel. So you can see here, pi cancels off. And of course, you can cancel off 1a, becomes then a squared, a squared. So now, once you simplify this, what do you get? This 3 and this 3 cancels. This cancels with this 3. And with this 3, this cancels. So you can do it mentally. Then, instead of writing a lot of steps, in one step, try to do the question. Of course, you all can take your own time and solve it, taking step by step, but this is the easiest way. So now, what do you get? You get 2a squared rho pbg minus what? Now, 3 times 3, because this 3 has to be multiplied by this 3, right? So then 3 times 3 gives you 9. So 9 eta v y is there? Yeah. And here we have what? 2a squared rho wg. And then we have 2a squared rho pb a. Now what can I do? I can actually divide by 2a squared. Okay, and of course I can divide by 2a squared rho pb. But I'm going to make a small rearrangement before that. I'm going to take these two together. So what do I get? I can take 2a squared g out and write rho pb minus rho w, right? Minus 9 eta vy equals what? 2a squared rho pb. Okay. Now I'm going to divide by what? 2a squared rho pb 2a squared rho pb, 2a squared rho pb. What do you see? This entire term cancels off. Okay, and then this cancels off with this. But then g rho pb over rho pb. I'm simplifying this because some of you all may be having trouble with simplification. So you can divide this rho pb by rho pb itself, and rho w by rho pb itself. So then what do you get? Minus rho w over rho pb minus 9 eta vy 2a squared rho pb is equal to what? A. Okay, so this is 1, as you can see. So g times what? 1 minus rho w over rho pb minus 9 eta vy divided by 2a squared rho pb equals A. This A is the acceleration in the y direction. Is this understood?
Yes.
Who got the answer for this?
Not me.
Okay, never mind. You learned something now. Right.
Sir, can I see that again?
Yeah, you want to confirm your answer?
Yeah. Yeah, sir, it's correct.
Brilliant. Okay, good thinking. Now, you don't have to do any of this. Now, really, you know that, right? Always when you use the wrong
Yeah.
method, I come and pretend you, but why did you do it that way? So, you don't have to write a single thing on the piece of paper. Nothing.
Hmm.
You can
Yeah,
use
sir.
this
So
argument.
for this part of question, I'll take your methods too, just like I always do.
Okay, so let's do it. Oh, it's a challenge now. Let's see. Any ideas are welcome before I give that method, right? Before I reveal the method, you all can suggest your answers. You're more than welcome. Okay, I'll start then. Of course, can the acceleration ever be zero in the horizontal direction? No. Why? Because there's a viscous force acting in the horizontal direction against the movement of the fluid, against the movement of the sphere. The sphere is trying to move forward, then there's a viscous force backwards, right? So if there is an external unbalanced force, there is what? Definitely an acceleration, right? So which means I can cancel off these answers and tell me, of course, there's an effect from what? The viscous force, right? There's definitely an effect from the viscous force. Why? Because viscous force is acting upwards. You are going down. 6 phi r, 6 phi a, eta vy. So there is an effect from the viscous force. If there's an effect from the viscous force on the resultant force, because on the resultant force, in that expression, of course, we are going to put what? The viscous force. If we are going to substitute the viscous force in the resultant force expression in order to calculate the acceleration in the vertical direction, eta should be there. Coefficient of viscosity should definitely be there. Answers that do not have eta have to be removed. This goes, and this goes. The only possible answer we can get is what? 1. Did you understand?
That is very straightforward, sir.
Yeah, sir.
Yes.
Why did you suffer? Mm-hmm. Right? So without writing a single thing, can get the answer. See all this energy which we spent. Of course, this is for you all to learn. That's why I explained this way. But of course, you all don't have to suffer that much, right? Okay. Sorry, I don't. Oh, this Gemini is responding to me. Gemini said, "I don't understand." I don't know why. Right? You all understood, right?
Yes, sir. Yes.
Yeah, sir.
So the parachutist. Okay, did anyone get the answer as the fourth one for this? Oh,
Oh
what?
my
Fifth one.
God, yes.
Which
Answer.
one? Wait, what is the answer you all got?
I didn't do.
It's okay. So let's see the answer.
So I really had no hope for this question because it's a
Really?
it's a graph, obviously. Obviously it's a graph, so you know.
So it's your trauma. So don't tend to
Yeah.
traumas like that. Don't worry, right? Um,
Okay.
you'll see the answer. It's
Rita is
actually the fifth
killing
one.
it today. Oh no, it's the fifth.
So we are going to get the answer as the fifth one. So I like to
Fifth.
see, yeah, the answer
So
is the
fourth
fifth
is
one.
not the answer.
No, it's not the
Oh,
answer.
okay, okay.
It's the fifth
You.
one.
Okay.
Okay. Okay, now listen to it. So we are going to enjoy this question. A parachutist bails out from a helicopter at time t equals 0. After a certain time, he opens his parachute and then reaches the ground. Which of the following graph best represents the variation of the vertical component of the velocity of the parachutist with time t? So we have to see how the vertical component of the velocity varies with time t. How do we start? So there's a helicopter. So the parachutist bails out, right? So he just comes out of the helicopter. So what is his initial velocity in the y direction? 0, right? He does not have any velocity in the y direction initially. So then, after a certain time, he opens the parachute. Which of the following graphs best represents the variation of the vertical component of the velocity of the parachutist with time t? Now you have to understand something very interesting. Okay, listen carefully. Let's see the passage of this man from the moment he bails out from the helicopter and lands upon the ground. What is the passage? Of course, initially, talking about situation one, when you look at situation one, if you look at the external unbalanced forces acting on the person, it's the weight. Up thrust is negligible, it's the weight basically. Right? Now tell me. So this weight is the external unbalanced force acting downwards upon the man. Which means what? This force provides an acceleration for the man. Right? So the man is going to accelerate downwards. But then there is what? A drag force. There's a viscous force acting upon the man. Remember, I told you that this viscous force is proportional to what? The velocity, some power of the velocity. In our questions, we saw it's v squared. So viscous force is proportional to v squared. So can you see, as the man keeps on accelerating, the viscous force keeps on increasing, right? As the man keeps on accelerating downwards, the viscous force keeps on increasing. Which means what? The drag force keeps on increasing. So when you think about a situation like 2, what can we say? Viscous force becomes substantial, or the drag force becomes substantial. It increases with the velocity, increases with the velocity. Okay? Now tell me, the greater the velocity I have, the greater will be the viscous force. Eventually, what's going to happen? The viscous force is going to balance the weight. So we are thinking about negligible upthrust. The density of air is also less. So now tell me, so we have then some situation where the force F upwards, viscous force F, will become equal to mg. We reach what? Terminal velocity. We reach terminal velocity. So then there is no external unbalanced force. Then we achieve a terminal velocity. So then the graph up to that extent, graph up to that situation is going to be like so. It's going to be like so, right? Because eventually the net force becomes zero. Net force becomes zero. So here in this situation, net force is zero. Then there is no acceleration. The gradient of the VT graph gives acceleration, right? Now tell me, what does the person do now? The moment he gains the terminal velocity, the parachutist is gonna open the parachute. It's very interesting. Let's dive into it now. What do you see? He opens the parachute. It's beautiful. When he opens the parachute, he's actually increasing the effective surface area, high surface area, high contact with the air molecules. Substantially high one. Because of the higher surface area, there's a substantially high viscous force. Substantially high viscous force. Then the viscous force overpowers the weight. Now here again, the upthrust is not considerable because parachutes do not have a big volume. Do you agree? I mean, of course, balloons have, right? Okay, so a parachute does not have a substantial volume, but rather it has a great surface area. Then, if it has a high surface area, it has a substantially high viscous force. Right? So then, are you all okay at that moment? That step?
Yeah, sir.
Yeah, sir.
Okay. Now tell me, isn't there a reversal of the forces? Now the viscous force becomes greater than what? mg. Then the parachutist, then the man is going to decelerate. The man is going to decelerate, right? He's going to decelerate. There's going to be a negative acceleration. Now the acceleration works upwards. What happens to the velocity of the man? So the man gained a particular velocity here, right? Now if there's a deceleration, what's going to happen, tell me? Yeah, what's going to happen? Now if there's a deceleration, the downward velocity that the man had before opening the parachute, now it starts to decrease. Now it starts to decrease. The man is going to decelerate. The downward velocity is going to decrease. The downward velocity is going to decrease. That is a very important thing for the parachutist. Now, now listen carefully. When the downward velocity decreases, what happens? This is a very important part. When the downward velocity decreases, what's going to happen? Now, the parachute is going down. Parachute is going down. Yeah, there was a very high, substantial viscous force. This viscous force is high for two reasons. One reason is the velocity is high. The other reason is area is high. Okay? But now you see, because you have a viscous force, the velocity keeps on decreasing. You're going down. Then the velocity keeps on decreasing. Then what happens? We know when the velocity decreases, the viscous force by itself also decreases. The viscous force by itself also decreases. Right? When the downward velocity decreases, what happens? The viscous force decreases. Viscous force decreases. Now, what happens when the viscous force decreases? Now, F minus mg was the upward acceleration or the downward deceleration, right? F minus mg was acting upwards, which was reducing our velocity. So when the downward velocity decreases, the viscous force decreases. When the viscous force decreases, what happens to the net force? Net force decreases. Net force decreases. What happens when the net force decreases? Therefore, deceleration decreases. Deceleration decreases. See how deeply we can get into a question. Deceleration decreases. That means the rate at which the downward velocity decreases. Right? Because the net force keeps on decreasing, the deceleration becomes smaller and smaller and smaller, which means what? Which means what? There's a possibility that now the viscous force will balance mg again, so that you will reach another terminal velocity now. Possibility of what? Possibility, depending on when you land on the ground, there's a possibility that F becomes equal to mg. Therefore, a new terminal velocity, a new terminal velocity. So there is a new terminal velocity. Now tell me, if I plot the graph like so, it explains all of this that I told you. We are kind of reaching a new terminal velocity. It's a possibility. And then in the graph, they have represented that it just suddenly becomes zero. What's the meaning of that? That is when the man lands upon the ground. So when the man lands upon the ground, what happens? There is this reaction from the ground is acting, and of course the weight mg downwards acting, right? So then tell me, at that moment, what happens? There is going to be a reaction from the ground that helps to decelerate the man further, right? So then that reaction from the man occurring upwards provides an upward acceleration or a downward deceleration, which reduces instantly the velocity of the man. And so in landing, suddenly his velocity becomes zero. It's a sudden decrease of the velocity zero. So we analyze this question deeply. Did you all understand this?
Yes, sir.
Yes,
It's
sir.
clear.
Okay. So figure shows a
Okay.
section of a long horizontal rectangular tube of height 0.016 meters having a large surface area and filled with what? A lubricating oil of viscosity 0.072 Pascal seconds. What is the force F required to drag a very thin plate P of area of 0.4 meters squared with a velocity 0.02 meters per second along the middle plane between the top and the bottom surfaces of the tube as shown in the figure? Now they have told you that this plate is very thin. What's the significance of that? Look at this plate, it's very thin. That means
Lesser
I can,
volume?
sorry?
Lesser volume, maybe? Not sure.
Yeah, but like the important thing is we can ignore the height contributed because of that object, right? So here 0.016 meters now. So here I can think of this height as what? 0.008 meters. And here also what? 0.008 meters. They're clear now, right? Otherwise, I can't take this gap to be 0.08 and this gap to be 0.008, right? I can't take that. So now tell me, how are the viscous forces occurring? Right? How are they occurring? When I'm trying to, when it's going with the velocity v forward, viscous force acts backwards. So we have viscous forces acting backwards. So if I want to maintain a constant velocity, I should provide a force F that is equal to what? 2 times simple F. Because viscous forces are acting considering this side as well as this side, right? Remember, we were talking about that on the surface, right? Remember, we're talking about a block that was moving on a liquid layer. There was a viscous force acting backwards. So here also we can see there are two surfaces to act on. Then the resultant force is 2F, right? And then 2F should be equal to what? Capital F, the force I apply. The force I apply should be equal to what? 2 simple F, right? Now tell me, F should be equal to what? 2 simple F. But what is this viscous force? I need to think about what? Now see, what's the velocity here? 0. Velocity here is 0. So if I just draw it, just drawing this part, velocity here is v, but velocity here is 0. So we have a velocity gradient. So I can find the value of simple F, right? So what is simple F then? Yeah. What's the equation that we learned? Eta A delta V over delta D. So what's eta that they have given? How much is that? Could you all support me? 0.072, right?
Yes, sir. Yeah.
Okay. 0.072. And then what's A?
0.4.
4. Okay. Thank you. So 0.4 plus the velocity difference from V to 0, right?
0.
So V minus 0.
0.02.
0.02. Yeah. So 0.02 minus 0 is 0.02. What's the gap? 0.008.
0.016.
No, no. 0.008. We're talking about this gap, right?
Yeah, okay. That's where the problem is. Okay, sir.
Okay. So it'll be always aware of what you're drawing, what the depth is, right? Okay. I hope everybody understood why we're taking 0.008. Because the velocity distribution happens across a depth of 0.008, right? Okay. So now we have the viscous force. And we have two such viscous forces acting on that plate backwards. So we have two such viscous forces acting on that plate backwards. Therefore, the resultant force I have to apply forward is equal to what? 2 times simple F. So that means 2 times what? What is simple F? 0.072 times 0.4 times 0.02 divided by what? 0.008. Right? Now you have to simplify. How do you go about simplifying this?
So if we cut the 2 and 0.08 something.
Yeah, but that's also correct, Amaya. So also we can multiply by 1,000 both sides. Then it's easier. Like if I multiply up and down by 1,000, it seems easier. Why? If I multiply this by 1,000, this becomes what? 8. This becomes what? 20. This becomes 8 and this becomes 20, right? Okay?
Okay, so
And then, yeah. And now you see 2 times 0.4 is what? 0.8. 2 times 0.4 is 0.8. This 0.8 and 8 can be cancelled off. 0.1. 0.1 times 20 is what? 2. Then what do I have? I have 2 there. Right? Then I have 2 times 0.072, right?
yes.
which is 72 times 10 minus 3 into 2. But I think I had to multiply by something else as well. You see, it's 144 times 10 minus 3, which is what? 1.44 times 10 minus 1. No? Now correct? Okay. Newtons. Is that the answer?
So, yeah.
Okay. Now you see, it's a nice question. No? So you have to think about both sides of the plate. Right? Okay. What about this question? You have to think intuitively. I'm not going to go deeper into this. Can you tell me the answer intuitively? Can feel it now?
Third is the answer.
Third? No, can't be. Any other suggestions?
So I'm kind of still reading through it.
Yeah. Now see, in the middle it's what? V. The other plate is also moving with V over 2. So can it ever be 0 either? At the bottom?
No.
No. Whatever the answer that have 0, we have to remove. Right? Do you understand? For sure.
5. Diagram 5.
Yeah, exactly.
Fifth diagram.
Exactly. Fifth one. Here it should be 0 anyway. Should be 0 anyway, right? Why? Because this plate is not moving. The velocity of this plate is 0. Then the velocity of the liquid layer at this point is 0. But in the middle, we have what? What's the velocity in the middle? Right in the middle is V. So I have to mark it as V. But this plate is moving with V over 2. So there's an argument between those two, right? Then somewhere in between, we have to have a 0 velocity because they're in opposite directions, right? So now do you understand? And this can't be the answer
Yes.
anyway. This should be 0. This cannot be the answer. At this position, velocity is 0. So 4 cannot be the answer either. And this doesn't make sense at all. It's like this plate is only moving and this plate is at rest, kind of a thing, no? Which is incomplete. It's wrong. So the only possible answer is 5. Do you all see the argument now? Right? Everybody okay? I like to hear your voices. Right? Okay.
I'm okay with it.
So because I won't be able to continue this for too long, so whenever I can, I'm supporting y'all. So let's try to make maximum use of this, right? Okay.
Okay.
Now so I hope you all have the question. So I'm going to discuss this essay now. Going to go one by one. So let's see what is that essay asking from you. Okay, so it says a laminar flow of a viscous liquid is maintained on a stationary horizontal plate. The top layer of the liquid is moving with a velocity v, and the stationary bottom layer is at a depth d. Okay. If the coefficient of viscosity of the liquid is eta, write down an expression for the force F that has to be applied on the surface of an area A of the top layer. It's very simple, right? The topmost layer is going to have a velocity of v. The bottommost layer is going to have a velocity of 0. So here it's 0. Then the velocity gradient is going to be like this. It's going to go from v to 0, right? Now what can we say? We know velocity gradient is what? Delta v over delta t, that is equal to v minus 0 over d. Now F equals what then? Eta a delta v over delta t. We get what? Eta into a. What's the velocity difference? V. Gap is d. That's the answer. Show in a diagram using arrows the variation of the velocities of the intermediate layers. We have already done it. Then, part 3. A person pushes a block of 0.5 kilograms on a horizontal floor. When a horizontal force 0.25 newtons is applied on the block, it attains a constant velocity of 0.01 meters per second. Okay. If a thin layer of an oil is applied on the floor, the horizontal force required to push the block with the same velocity 0.01 meters per second reduces to 0.05. The contact area of the block is 1 times 10 minus 2 meters squared, and the thickness of the oil layer is 1 millimeter. So it's a very simple question. So we have a thickness of how much? 1 millimeter. Thickness is 1 millimeter. So what's the mass that we have? 0.5 kilograms. Now we have to see the viscous force acting. Right? Viscous force acting. So you know the reaction here is equal to the weight. Reaction is equal to what? 5 newtons. Now when you think about this viscous force, I know the equation for it. Eta A delta V over delta D. So what is eta now? What's eta? They're given us that, right? Or are they asking us to find it? They're asking us to find it, right? So that means we know the viscous force. How do we know the viscous force? Now they have said to maintain a constant velocity of 0.01 meters per second, right? We are trying to maintain a constant velocity of how much? 0.01 meters per second. We're trying to maintain a constant velocity of this much. That means the forward force that we apply, F dash, has to become equal to what? The backward viscous force. The force that you apply. Force that you apply should be equal to what? The viscous force. When there is no resultant force, the velocity remains constant. Right? That means the viscous force here is equal to the applied force, that is 0.05. So now we have a viscous force of 0.05 newtons. And then what is eta? That's what we have to find out. Because the area, effective area of contact of the block is 1 times 10 minus 2. And then what's the velocity difference? It's 0.01 minus 0. This layer is going to have velocity of 0.01. The bottom layer is 0. Then 0.01 minus 0 divided by what? The gap. Gap is 1 millimeter. I need to convert that into meters. 1 times 10 minus 3 meters. Then you see this is going to be 10. And this 10 and this 0.01 becomes 0.1. Then what happens? We can multiply both sides by 10. Then 0.05 times 10 is 0.5 Pascal seconds is equal to what? Eta. Okay? Understood?
Yeah, sir, understood.
Okay.
Yeah.
So then we are going to come to what? Part B. Find the effective coefficient of sliding friction between the block and the flow after applying the oil layer. So now we are think as if we are applying F equals mu R. Because we're thinking about the situation as if, okay, let's forget about everything and apply what? F equals mu R. Because that's the only equation we need to find friction in terms of what? Coefficient of friction. So what's the force? 0.05. What's mu? That's what we're going to find out. What's the reaction? 5. Very simple question. So you get 0.01. 0.01 becomes equal to mu. Actually, this F is what? The dynamic friction. Therefore, this mu that we have found out is what? Dynamic frictional coefficient. Coefficient of dynamic friction. Right? And yeah. Now, okay. Part C. What is the energy that can be saved during 1 second due to the application of the oil layer? Now, what's the work done in 1 second? That's power, right? Now, when you have a force F that takes the object to a displacement of S, work done is equal to what? Force times displacement. Change in work done is equal to what? Force times the change in displacement. So now what I can do is what? I can divide work done by the time taken, both sides. So if you have a constant force, what is the result that we get? Can you all see that? What's the result that we get? When you divide both sides by delta t, we get the power here. So power, rate of doing work is power. So power, and then what is rate of change of displacement? That is velocity, right? It's velocity. So then you get an expression which is what? Power equals what? Power equals force times velocity. Power equals force times velocity. All right. Now tell me, when you look at situation C, what is the energy that can be saved during 1 second due to the application of the oil layer? Now we can think about the energy we spent per second, right? Before the application of the oil layer. So what was that? What was the previous force? What was the previous force?
0.25.
25. Yeah, 0.25. And previous velocity? 0.01. It's the same, no, as the new one.
Yes.
This is Pi. That's Pf. That's final power. That means after we apply the oil layer, then what happened? The force became 0.05, but the velocity 0.01. If I subtract Pi from Pf, what do I get? 0.01 out, and then what? 0.25 minus 0.05. Then I get 0.01 times what? 0.20. Right? So 2 times 10 minus 1 times what? 10 minus 2. And we get 2 times 10 minus 3 joules per second.
Yeah, so it'll be 0.002 joules, right?
Yeah. So the answer is what? 0.002 joules. Okay. Then, if you think about the last statement, you all can't do it because you all have not done surface tension. In order to lift the block from the oil layered flow, in addition to the weight of the block, a vertical force has to be applied upwards on the block. Explain the reason for this. That's actually because of surface tension forces, which we'll be discussing. Okay, the questions come to an end. So that was like a paper discussion, no? Right?
Yeah.
So, Poiseuille's formula. What's this formula? Okay, so what we do is we think about what? A horizontal narrow tube like this. We think about a horizontal narrow tube like so. The radius is simple r. Let's say radius of the tube is simple r. And I'm considering a length of delta L. And here I'm saying the pressure is P plus delta P. Here the pressure is P. So the pressure difference is then delta P. So I'm going to consider a particular cross-sectional area A. So the fluid moves like so. Streamlined motion, it's steady flow. All those conditions are met. The flow is like so. Now you know the rate of flow of a fluid that you have done, right? What's the rate of flow of a fluid? Delta Q over delta T. That's equal to AV, right? Rate of flow of the fluid. So rate of flow of the fluid is equal to the area times the velocity. Okay, right. So now tell me, when you look at this fluid, if you think about the rate of flow of the fluid, that is how much of a volume flows in 1 second, right? It actually depends on several factors, just like we discussed in Stokes' law. In Poisson's equation, we're thinking about some factors affecting this rate of flow of the fluid. So delta Q over delta T is how much of a volume that flows per second. That is proportional to what? The radius into some power. And what? Pressure difference over the length. That means the pressure gradient into some power. And what? Eta to some power. So as usual, you all can use what? Dimensional analysis, right? And you can do this. You can get the answers for x, y, and z. It's a simple matter, so I'm not going to explain that. And you'll find out the k value for this is 5 over 8. So the rate of flow of the fluid, actually, when you write the equation eventually, you will see, once you find x, y, and z, it's equal to what? 5 over 8 r to the power 4 delta p over delta L over eta. I think we have not done fluid dynamics, so I will be explaining this part in fluid dynamics. So for now, just
Yes,
remember,
sir.
area times the velocity gives you the volume flow rate. Right? Now, this is what? Poisson's equation. Right? Very important equation. Right? It's very important equation. This is the pressure gradient. Now, of course, we know that delta Q over delta T can also be written as what? Area times the velocity. That's equal to what? Pi r to the power 4 eta 8 delta P over delta L. So I'm going to use this to construct another equation of convenience that you all can use for MCQs as well. Right? So these lessons are very easy. Try to score marks from these lessons. Now, if I think of a tube, so I'm going to go for a tube, right? When you think of a tube like that, it's cylindrical, a cylindrical tube. Then the area is pi r squared if the radius is r. If the radius is r, then I can say the area is pi r squared. Okay, so now I can substitute to this equation phi r squared into velocity is equal to 5 over 8 r to the power 4 over eta delta p over delta L. This phi and this phi cancels off. And this cancels off, so r to the power 2. Which means what? Velocity equals r to the power 2, 8 eta delta p over delta L. That's a beautiful equation that we just constructed now. It's not always valid. It's valid for this kind of a shape. Right? I hope that's clear as well. Okay. So, can everybody hear me?
Yes, sir. So I
Yes,
think
sir.
it will be a bit more clear for me after we do fluid dynamics, right?
Yeah. Others are okay, right? Okay.
Yeah.
So when the pressure difference between the two ends of the tube is increased more and more, what's going to happen? When you increase the pressure difference more and more, there will be a stage where the motion will become turbulent. The fluid motion becomes turbulent at some moment. The velocity in which this transformation happens is known as what? The critical velocity, beyond which we say Poisson's formula is no longer valid. So we can't have huge pressure differences, beyond which it's not valid, right? So I feel I will give you some homework, in some questions, so I can try. So I want you all to try the 2016 essay, A-level essay, 2016 essay from Viscosity. Do this. And of course, there are many essays you can find out from your past paper books and do. Model questions, I'll try to do a paper for you all, so we can cover some model questions as well. So then, hopefully, we'll meet on what? Friday, right? So did everybody understand the lesson?
Yes, sir. Except for the last
Yeah.
one.
Today you all are very silent, no? Everybody's very silent today.
Yeah,
Yeah.
sir. We all
Yeah.
were very eager
Yeah.
about the method we're gonna give.
What?
And then in the 2-minute break, I was just thinking about the question because I didn't do it.
Oh, okay. Right.
Yeah.